All right, let's go ahead and get started. It's time for us to kind of move on to the next topic, which is recursion. I have that quote that I really like down there. I don't know if it's an actual real quote or not, but to understand recursion, one must first understand recursion. Again, I cannot say for certain that is a real quote. Thank you for the sympathy laugh there. In terms of where we are and what we're going to be studying, really the importance of recursion is not necessarily as an additional tool in our bag of problem-solving tools, but it does, I think, provide nice opportunities to really illustrate the problem-solving process, to do that sort of computational thinking, which we've done this semester, and you'll have to keep doing to grow and be stronger in that area. And having recursive solutions and kind of dictated that a solution must be a recursive one can really help strengthen you there as well. The real problem-solving strategy comes in place when you get to decide whether or not a recursive solution makes sense for you or not. And as we'll talk about, it's very rare that one must have a recursive solution to a problem, but sometimes it can lead to a very clean, nice, and easy to understand problem and a solution. And we'll go through a few illustrative examples of that. In terms of logistics with where we are in the semester, I can quickly bring up Canvas here and our schedule view here. Well, I hope everyone enjoyed their Thanksgiving break, but we're really almost done here, right? This is our last week 14. Next week is that kind of quiet week, but we just kind of continue on with what we are doing since we don't have a final exam in this class. Another way to think about our schedule is basically we have 2 weeks for your final project. So that'll be that Monday of exam week. I did a quick review of all the projects. Some are really chugging along. Others, as far as I can tell, have not gotten started yet. And you really do need to be getting started in earnest. You don't want to try a last-minute sprint. I think you'll just be disappointed with the results and with the outcome. So start to make progress today if you have not done so. In general, there has to be a design aspect of it. You don't want to just start typing like we never want to just start randomly typing into our editor. But when you need guidance as to what part to work on next, definitely go back and look back to your rubric. What did you propose you were going to do? What do you have to be able to demonstrate to receive a certain number of points for this or that attribute? And kind of work from there. Okay, I need to get this menu working in this program because that's worth 40 points in my rubric. I should get going on it. And maybe 2 people on the team just dedicate themselves to being able to check that box and say you have that part working here. But it takes time, and 2 weeks is not a ton of time. But if you do dedicate yourself starting today, you can get your project done for all the different projects that were proposed starting today. Let's talk recursion. At a high level, all recursion is, it's a type of algorithm or implementation in which we have the same type of computation that occurs repeatedly. Now, we've already seen a way to structure our code when we have the same type of computation that occurs repeatedly. That was the whole point of having loops, right? We want to do something a certain fixed number of times, or until a certain condition is met. We have a for loop or a while loop that are designed and intended explicitly for that purpose. So recursion is similar to that, but different in that our approach tends to look a little different in terms of how we implement it. And what I want you to remember from recursion is this whole concept of divide and conquer, where you're going to have 2 classes of input. You're going to have one class of input, meaning one value or set of values for your input, for which you can just explicitly solve the problem. That's what's known as the base case. Small is kind of a fuzzy word to use here, but you have a certain set of values for which the answer, the code needed for this, it's going to return this particular value. I can just write that code and solve the problem for that base case. Then you have the general case where your problem is potentially, quote unquote, larger here. That's the recursive case. The idea is that you take that larger problem and then you subdivide that into successively smaller subproblems and then ultimately combine back the results. So you have your Matryoshka doll way of looking at it. In order to solve this problem, you first solve this problem and combine the results. To solve this problem, you then solve this problem, to solve this problem, and so forth, until eventually you get to your base case where you can't subdivide the problem, or it doesn't make sense to subdivide the problem any further, and then you kind of combine the results all the way back up. That is a little, hand-wavy and vague. I think as we see it in practice, what it tends to mean for us is we write a function that handles those 2 cases. There'll be an if statement of some sort. It'll either determine this input value is a set of values or a value for which I know the answer, I just return the answer. That is the base case. Otherwise, if it's not in the base case, I'm going to combine the problem into a series of subproblems to combine the results. I'm going to call that function itself and return the results back and combine it to get the final result we are interested in. Here's one such recursive example. Those of you who've looked at the corresponding reading have seen something similar to this. If I want to perform integer exponentiation using only the basic arithmetic operator, so that is a synthetic problem, but it shows how one can implement via a recursive solution. The key recursive algorithm here is to recognize that to calculate k to the I, one such way we could do so is to take the value of k and multiply it by k to the I minus 1. That would be the recursive case. We take the larger problem, calculating k to the I, and break it down into solving k to the I minus 1, and then combine that result by multiplying it with k. That is the recursive case. Eventually, as we go from I, and this only would work for integers, as we go from I to I minus 1 to I minus 2, etc., all the way down, we get to I equals 0, and then that could be our base case, because for integers, calculating k to the 0 is always going to return a value of 1. So logically, we can kind of visualize the Matryoshka dolls here, the recursion happening, that if we want to calculate 3 to the power of 4, we could do so by instead calculating 3 times 3 to the third. To calculate 3 to the third, we can then calculate 3 times 3 to the 2, etc., until we finally get to our base case, which is just 3 to the 0 equal to 1, and then we kind of make our way back and combine all those sub-problems together to get our final result here. In code, it winds up looking very similar to the mathematical expression for it. We would likely have an if statement just determining if we are in the base case or not. Typically, that would happen before the recursive case in terms of how we would typically want to implement this. We would take our function, integer exponentiation, takes the base, takes an exponent as input. We would check. A good comment for this would be, is this the base case? If it's the base case, we just need to return a value of 1. If it's not the base case, we want to return k times k to the I minus 1, or base times the result of calculating base to the power exponent minus 1. Quickly just show that, what that looks like in action. So for just this example, I say base is 3, exponent is 17, and just a little bit of debugging printf here where we want to calculate 3 to the 17th power equals whatever is returned when we then call that function. For debugging purposes, and you will find that you have to do this quite commonly when writing recursive code versus arbitrary functions that are just called once, it's pretty helpful to have this kind of sanity check here where you are checking that currently I'm inside that function and that's the current inputs that I'm working with in that function. So that's not needed for correctness of this code, but just to be able to kind of track and trace what functions are getting called. Let's walk through it one more time. We have the base case. If I, or the exponent, is equal to 0, just return 1. We're done. We've gotten to the smallest little Matryoshka doll. We don't have to go recursively any further. We could also, actually, if we had wanted to, we could have stopped when exponent equals 1. If exponent's equal to 1, what should we return? Yeah, we could have also done it this way. So both are valid. I don't want to quibble which approach is better than the other, but at least this exponent operator, as you go from k to the I to k to the I minus 1 and all the way down, you do wind up in that final case where you get I equals 0, and you can return a value of 1. If the exponent is not equal to 0, then we are basically calculating, as the equation showed, k times k to the I minus 1. And this is what makes it a recursive solution, right? We are saying to get the result of calling that int exp function, call that int exp function again, and take the result of that call and combine it, and all we're doing to combine it is just multiplying the result times base. If you had wanted to create a temporary variable to store the result of that function call, that also would have been fine. It doesn't need to be purely recursive as this version is showing here. But take the result of that function call, combine it with the current value that I have inside my function, and return that as my result for the function call. Without that printf, it can be pretty hard to debug what's happening. With that printf on line 5 here, as we calculate 3 to the 17, we should see the inside printouts, right? And this printf, while it's the first printf we encounter as we're executing the code, that printf takes as of one of the values the result of that int exp function being executed, right? And just directly takes that as the integer to print out. So actually the first set of printf statements we actually see are these that are the ones that are inside that function call. So we're inside 3 to the 17, consequently then we're inside 3 to the 16, our I minus 1 values, all until we get to the point we are now at 3 to the 0. That returns 1. We don't really see all those values getting kind of returned along the way. If we were to add another printf statement, we would have to create a temporary variable and store it. If we were to add another printf statement, we would see the return of all those functions as well. But at least we can see all the calling from 3 to the 17 all the way down to 3 to the 0. Those values then return in kind to get our final value back out here. I'm going to hesitate from claiming that a particular recursive or non-recursive solution is good or bad. I don't think there's no point in making that kind of value judgment. Just understanding it as a possible tool that we can use to solve a particular class of problems. The examples today, I think as we look at them, it's totally fine and it's great if your mind is looking at that and saying, oh, I don't need to use recursion for that. Because the answer is almost always that is true. So that's fine. Unless it's a class assignment, no one will ever force you to have a recursive, solution for a problem. But I think on Wednesday and even going into Friday, we'll look at a couple of problems once we get a little bit more comfortable with this approach, for which, yes, one could work through a non-recursive solution for the problem. It's going to be harder. I think we can at least claim that. For this one, calculating k to the ith power, it's not that clear that recursion gives us any value other than it's a nice straightforward example that we can visualize what's happening in our recursive solution. Let's kind of circle back to what happens when we call our functions, right? We've talked about this a couple of times in a couple of different contexts, and it's relevant here, and it kind of lays more bare the kind of issues we see when we call functions and how that relates to a memory. Every time we call any function, the compiler, in some conjunction with the operating system, is going to allocate some memory relative and local for that function. This goes to our discussion of scope as well, right? I have a variable called I in one function, and it's different than a variable called I in a different function. They have the same name, they have local scope. The way we can have that and can support that is by having local memory for each of our functions as well. Every time we call a function, the compiler can determine how much memory did that function actually need. It stores things like the variables that are local to that function, as well as some other stuff to kind of keep track of where we are in the program, and it puts it on this data structure that we've been referring to and is typically referred to as the stack, which grows and it shrinks over time based on what our particular function call pattern is. We've talked about function foo, called function bar, called function baz, etc., and how that call stack grows and then shrinks over time. That's exactly the same thing that happens when we have our recursive calls as well. It just starts to become a little bit harder to visualize, and understanding the scope also becomes a little bit harder for us to appreciate because it's all the same function. There's no different named variable or different named function. It's the same function, but it is a different invocation of that same function. So the example in the replit was 3 to the 17th. Even if we just want to visualize 3 to the 4th power here, we get the corresponding function call graph and the corresponding stack layout that grows and shrinks over time. Function main calls my integer exponent function here. That's the black arrows we have here in this diagram. 3 to the 4, which calls 3 to the 3, etc., until we get to 3 to the 0. Finally, 3 to the 0 returns back to 3 to the 1, which returns back to 3 to the 2, etc., all the way back to our function main here. So for that reason, if we go back to the code here, we have these inputs of base and exponent, and the scope of that is still local to that function. It's not a global variable just because we're calling it recursively, but the value we have for base and exponent is local to that particular calling of that function. So exponent, when we call it with 17, that value is 17 when we call that function from main. But now when we call it again with exponent minus 1, there'll be another stack of variables for 3 to the 16 or 3 to the 3, whatever we have in this example here, that uses the same variable names. Those variables still have local scope, but they're going to be placed on the next frame of the stack as we build our function call stack up. So that can be a little hard to kind of wrap your mind around as you're trying to debug what is happening. And what works for me, at least, and this is really true for any of the debugging that we do, anyone who's been in my office hours has seen that when I'm uncertain of what's happening in my code, I just stop and add more prints and check the actual values of my variables. So for me, while this example is about as trivial as you can get for a recursive example, just knowing where I am at any given point in time is pretty important for me to be able to appreciate and understand where exactly I am in the code and what the value I have for my particular variables. Because there aren't a lot of variables in the actual code. There's base and there's exponent. That's basically it, right? But there's the base and the exponent defined in main. That would also get placed on the stack. That's that first green box we have up here. And then there's the base and the exponent corresponding to the input arguments for this function. And that itself is also going to keep changing because it'll be 3 and then 4 and then 3 and then 3 and then 3 and then 2, etc. Compilers can be pretty clever at the end of the day in terms of what actually gets put on the stack or not. It may be smart enough, a good compiler, to detect that, well, exponent changes, because we go from exponent to exponent minus 1. Base never actually changes, so maybe base doesn't actually get placed on the stack. But conceptually, at least, that is what gets put on the stack. All the variables needed to execute that particular function for that particular series of function calls that we have here. The only difference now with this recursive solution is it's the same type of information that's getting kind of copied over and over and over again. And so it may or may not be a little bit harder to debug what is happening in terms of what's on our stack and what the values we have for our local variables of that function. But it is no different. You do have to sometimes watch out. This is a small lame joke about Stack Overflow, that when we have a regular function main, calls function bar, calls function whatever, we do have a call stack, and it can be a reasonably deep call stack here. But there tends to be a limit, and that limit's a function of you as a programmer. How many functions can I think of? What functions can I possibly have calling any other functions? A function call stack of size 30 is pretty deep. It's a pretty complex piece of software that you're running. Whereas when I have an exponential, or excuse me, a recursive function here, it takes nothing to change that exponent to 1700 versus 17 here, right? And this is compiler dependent, and I should have checked it, but I didn't. I don't know if it's going to have any problem with this or not. Didn't seem to have any problem with it whatsoever. But the actual call stack then is significantly deeper now, right? Now it's 1700 function calls deep, and I didn't change anything in my program at all, right? I just changed the exponent that I was using here for that particular usage of that function. So while technically we always have to worry about potentially having too many things on our stack, when it's a recursive function that we're working with, it's much more likely to potentially happen, because without really thinking too deeply about it, you could have set up a problem for which the call stack could be extremely large. There's all sorts of things we can do to potentially improve this particular function for exponentiation. We can explore a couple of those things. One thing we could consider is the fact that, well, if our exponent is even, one different way of doing the recursive case would be to calculate that k to the I. Yes, it's equal to k times k to the I minus 1, but if I is even, it's also equal to k times k, or k squared, to the I divided by 2. That's just how integer exponents, or all exponents basically work, because 3 to the 4 is the same as 9 squared, right? And 9 squared is actually the same as 81 to the first power. That's a pretty modest modification to our program, but there's all sorts of things in cryptographic and other application where you may have 1,000 plus bit numbers and you're doing integer exponentiation with those numbers. So we can certainly build a version of this program that would actually then have two different potential recursive cases here, just to show that it's not always as straightforward as base case followed by recursive case. In this version, and I actually have it here and we'll just uncomment it, what we would be checking is we would still have our base case. If it's e to the 0 or k to the 0, just return 1, we're done. Then we have a modified recursive case, which is if our exponent is even, that's what exponent mod 2 equals 0 would be checking, right? If we have 3 to the 4th power, instead of going 3 to the 3 and then 3 to the 2 and then 3 to the 1, we recognize that 3 squared is 9, and we can do 9 squared versus 3 to the 4th power. A lot of different ways we can encode that, but one such way we could do so is by instead returning now recursively not 3 to the 4, but 9 squared instead. Take base times base as our new base and go to the exponent divided by 2 power. But if it's not, even if it's odd, then we can go back to our basic case that we have here. For 3 to the 17, that should be something sufficient for us to test this example with. Exponent will be 17 when we start, so it'll trigger this case. We'll go from 3 to the 17 to calculating 3 to the 16. But at that point now, once you have an even exponent, you'll be kind of even the rest of the way down, right? We'll then have 3 to the 8th, then 3 to the 4th, then 3 squared, and then finally 3 to the first power. And we can see that to calculate the same value here, it's kind of interesting. Now our base and our exponent are changing. 3 to the 17th, 3 to the 16th, now 3 squared to the 8th, 3 squared squared to the 4th, etc. And that's, 3 squared, 3 to the 4th, 3 to the 8th, and I guess 3 to the 16th, then to the 1, and then finally to the 0th power back out. Gets you the same result. Again, is one solution, quote unquote, better than the other? It's not necessarily a value judgment we can easily necessarily make. There's what's happening on the compiler side, how much we care about raw performance versus perhaps how much memory usage the program is using. How easy is it for us as programmers to understand what the program is doing? But it's certainly a different way of doing the recursion solution for that particular problem. A third potential solution would be just to recognize that, as I mentioned, we don't always need to, we certainly don't ever truly need to use recursion. And very often, for every recursive solution, including for this k times k to the I minus 1 type of problem for integer exponentiation, we can also just do an iterative solution as well. And that's what this little simple for loop would be doing, right? Well, recognizing we have exponent is 17, that just means I have to multiply base 17 times by itself, right? Just take the value, start with our base case of result equals 1, and multiply by 3 17 times until I get my final result back out. And that approach is perfectly fine as well, and it should give us the same exact result back out. And so that point, if you want to make it, is perfectly valid. Before I talk about Fibonacci, I want to bring up this as a slide here. Couldn't we have just done these with a for loop instead? And the answer is yes. Almost always the answer is yes. I say always, I think that is strictly true. Without too much difficulty, you can create an iterative version of a recursive algorithm and vice versa. And something that I was playing around with when kind of exploring this topic is that compilers are pretty amazing and sometimes can even do this type of optimization for you. Have we looked at the Compiler Explorer website yet this semester? Briefly earlier in the semester. This is godbolt.org. It's just the guy's last name. It sounds like a very cool website, but that's just the guy's name. And it's just a very quick way to explore what a compiler will generate for a particular block of code. For your programming careers, until maybe you get really deep into like the embedded side of things, you generally kind of just trust that your compiler is correct. But when you have a performance problem or something is not generating the code that you think it should be generating, or other things are getting optimized away, you may see some value. You can always tell your compiler itself to generate this type of output for you. This is just a nice website because you can kind of just directly explore the output of all sorts of different compilers targeting all sorts of different architectures. This is just, they're labeled based on the architecture and the version and the type of compiler. So targeting an Intel 64-bit microarchitecture using well-known GCC compiler for this same exact code that we just did here, or a version of this code here. Left tab is your C or C++ or whatever code you want to have as input. That middle tab, which I can actually expand out a little bit so you can see it a bit better, is the generated assembly code. And eventually, if you become interested in looking at microarchitecture level details, you'll start to become pretty fluent in looking at assembly code. We don't have to be, and the nice thing about this Compiler Explorer is the colors are a little washed out. It looks a lot better on my screen. It even kind of color codes it for you is what it's trying to do here. That there's some multiplication going on as well as a recursive function call here. Well, it highlights it for you, right? And that's that line 7 of our C code. And that's corresponding to this block of our assembly code here. Move instructions and load instructions. We don't have to worry really at all about that in this class. But I think we can kind of squint at it and see where the recursive thing is happening here. And that's a sufficient fluency that we need. We can squint at assembly code and kind of guess at what it's doing. It's inside that function. It's going to call that same function, and it's going to take the result of that function, and it's going to multiply it to get that next value. So you can kind of see where that recursive call is happening. Kind of, sort of. That's fine. That's sufficient outcome for that. We can see what that looks like from an assembly perspective. Well, the other input to this, as we call our compiler, is what type of optimizations do we want the compiler to do? In this case, I passed in dash capital O0, dash O for optimization and 0 for the amount of optimization, and that's telling the compiler, hey, I don't trust my code. I don't want you to be clever. Just give me just the most vanilla implementation possible. There's O1, O2, O3. There's a whole laundry suite of optimizations we can pass in. If I just pass in dash O2, which is usually considered a reasonable and sane amount of optimizations, to the extent where that's sort of a default when you're running a compiler, it'll pass the equivalent of O2. Well, what happened? It's hard to see. Again, this is assembly code, and we are not experts in assembly, and we don't have to be. What happened in our code? On the left, it didn't change. That's still our input C code. In the right, well, certain things are a lot less highlighted here, but the main block for our function is still that line 7, right? That's our recursive case. There's nothing highlighted in yellow here except for that single I multiplication instruction. And for what it's worth, I'll just walk through what that's doing. Multiply, subtract 1 from an iterator, and loop back, jump not equal, loop back to that label here. So what did it do? The compiler took that recursive code we provided it and converted it into a for loop for us, which just kind of blows my mind a little bit. Like, how is it able to determine an equivalency? But it's able to, whether it's some clever pattern matching or whether it can kind of algebraically determine what the result should be. And the only difference was, again, the C source code didn't change at all. We just changed what optimization we passed to it. We went from kind of a straightforward translation to our assembly code where it is doing the recursive call. That's what's happening on line 17 here, to now, with a reasonable level of optimization, it's gotten rid of that entirely. So just to reiterate what I already kind of mentioned to start things off here, I think understanding recursion as just like an extra topic for us to learn this semester still is pretty valuable. It's a good way to think about how to decompose problems. It is another tool in your tool belt of things to be able to attack problems, to solve things. But this point is valid, equally valid, which is we can generally have an iterative version of a recursive code and generally vice versa. And so today this may all seem kind of synthetic, and it usually is, right? But then maybe on Wednesday and Friday we'll look at a couple problems for which, again, you could write an iterative, a for loop solution for the same class of problems. But I think we'll find that the recursive solution has a kind of a cleanness and cleverness and simplicity to it that would not be there in the for loop equivalent of that function. Let's talk about this second example of the Fibonacci sequence. We've played around a little bit with that earlier in the semester, and we very briefly toyed around with the recursive version of it, but now let's do it properly. Familiar with the Fibonacci sequence? We start with 0 and 1, and then the next value in the sequence is the sum of the previous two sequences. So two values in the sequence, 0 and 1, we add them together to get 1. 1 and 1, we add them together to get 2. 1 and 2, we add them together to get 3. We can also implement that iteratively. We did it earlier in the semester as we were playing around with for loops. This also, just based on kind of the mathematical representation of the problem, directly leads to a recursive solution as well, right? To solve the value of f sub n, the nth term in the Fibonacci sequence, we just add the value of the n minus 1th term with the n minus 2nd term. And then also this gives us the base case as well. If that's our recursive case, the base case is if we're solving for f sub 0, just return 0. If we're solving for f sub 1, just return 1. And as we break out that code, hopefully you can just explicitly see both the base cases. In this example, there's 2 base cases, as well as just that sort of pure recursive case that we have here. Given an input value of n, and I made it a 64-bit int because I was trying to be clever. It's not super relevant to what we're doing here. Fibonacci sequences grow pretty quickly, as do exponents. For a given input of n, there's our little debug statement again. If n is 0 or 1, we just return the base case. We're done with the Matryoshka-Doll. But otherwise, calculate n minus 1 and n minus 2, and add those two results back together. And I made it as an input of argv for some reason. So we'll have to run that directly. If I want to then do main of the 10th Fibonacci number in the sequence, you can see then all the recursive calls that are happening here. And then the final value, which I don't know off the top of my head, returns back out that the 10th Fibonacci number is 55. If we're uncertain about that, we can always do like 6 or something like that. And that seems correct to me. So 0, 1, 1, 2, 3, 5, 8. N equals 6 gets us a value of 8 back out. As we start to run this for larger n's, and with a 64-bit integer, I cannot off the top of my head tell you how big of a value I can provide as an input for that, but we'll start with 128. You may start to see that it looks pretty slow. Compared to our integer exponent code, it's still going. For our purposes, that counts as pretty slow for our purposes. What's going on here? Just what do you see? Why does it look to be, it almost looks broken, right? It's not broken, but what's going on? That is definitely part of it. And there's no doubt that if I were just to comment out this line, this is really annoying though. Let's kill it. We gotta compile it again if I'm gonna comment that out. That is always definitely part of it. And I've talked about that, right? Print is actually a pretty complicated, printf is a pretty complicated, pretty slow function. Being aware of that, certainly when you go to time critical things, is always an important thing to remember. Even without it, yeah, it's still pretty darn slow. Yeah, and let me go back to, let me recompile it again and run it so you can see what's happening in our steady state here. Again, at a high level, they are doing something kind of different. I mean, integer exponentiation is different than Fibonacci. It's not that different, right? I mean, we have a base case for when the one input is equal to 0, and then we have a recursive case. We have a base case for when the one input is equal to 0, and then we have a recursive case. Whereas I think I did, it would overflow pretty quickly, but when we did a large integer exponentiation, this is gonna overflow, but we can still calculate it. Still, yeah, it overflowed, so it gave us the wrong result, but it's still calculated. It's still super quick, right? Took no time whatsoever at all, including with those printf statements. Whereas now, let me run it again with our Fibonacci to the same power. It looks kind of stuck, right? Your point, I think your observation is valid. I plugged in 128 for Fibonacci, and well, our eyes can kind of deceive us when we're looking at a stream of printf statements, so you have to pause it if you really want to know what's happening, or just pipe the result to a file if you really want to analyze what's happening. But it looks like it's just stuck calculating Fibonacci of 5, 4, 0, 1, 2 over and over and over and over again. Well, it's because it is. Looking at just Fibonacci of 6 and its own either call stack or it's just tree of functions that are being called kind of tells you part of the story of why that's running so slowly. That figure is also not showing up super great on this slide, but what we have is the call stack. Assuming I called n equals 6 and called that function for n equals 6, what does it do? Well, calculates f of n minus 1 plus f of n minus 2. So recursively, it calls Fibonacci of 5 and Fibonacci of 4. That's now two types of like branches of recursion here, but otherwise it's exactly the same as our integer exponentiation implementation. When I call Fibonacci of 5, that's n equals 5. It then calls n equals 4 and n equals 3. When I call n equals 4, it calls n equals 3 and n equals 2. What's happening? Why is this so inefficient based on that kind of call stack?
When it calculates a value, when it calculates 5, it moves into the next value, it recalculates 5.
Yeah, and in this case, because of 5, it's only doing it once, but 4 or 3 or 2 is a good example. It's just doing it over and over and over again. And I think it's exponential how many times it's going to keep recalculating Fibonacci of 1, because for every possibility, for 128, it's going to do it. For 127, it's going to do it. It's going to keep calculating these smaller values over and over and over again. Just look at how many times fib of 1 shows up on here. 1, 2, 3, seems wrong. I didn't actually include all the cases. Should be 1, 2, I didn't include all the, should be, for every single one of these nodes, it should be calculating Fibonacci of 1. So it should be basically 2 to the n times it's going to calculate Fibonacci of 1. That code is still going. It may never stop. That's potentially the downside, potentially, of a recursive implementation, but there's also workarounds for this kind of problem as well. And one such workaround is to recognize, and let's kill that just for the sake of not running out of time here today. One such workaround, this technique, you may see the formal name of memoization. I don't really like the term. The idea is that once I've calculated Fibonacci of 3, I don't ever need to do it again. I just need to keep track of that value. What was then a recursive implementation for Fibonacci of 3 can just be replaced with a cheat sheet, a lookup, a memo. I write down the result of what Fibonacci of 3 was, and the next time I need to calculate Fibonacci of 3, I just skip it and say, oh, I already know what it is. Let me grab that particular value. It's referred to as memoization. It's a type of a technique necessary for certain recursive implementations. It requires us to be thinking about how much space we potentially have to have allocated. And with a recursive implementation, we may need to have some sort of global memory to kind of keep track of that. But we could probably build such a thing. So again, the idea is, if we've already calculated a value before, let's not calculate it again. So that does require us to have some mechanism by which we store some temporary results value here. And we don't know how much space we need for that until we know how big n is. So this is going to have to be some sort of dynamic memory allocation that we're going to do here. And we need to keep track of how much data that we actually have stored here. So we've grabbed the value of n. We know we want to calculate n values. We then want to allocate n entries in this big cheat sheet, this big lookup table, to keep track of the values of Fibonacci that have already previously been calculated. Again, we don't know how big n is until we read it in from the user. What function do we need to do to allocate an array of size n? We need to dynamically memory allocate. We need to use malloc for that. That pointer is called results. There's the 3 parts of the malloc. Usually there's the cast, where we specify the result's going to be a pointer to a 64-bit unsigned integer. We have the actual, in this case, let's initialize it all to 0 so we don't screw this up. Calloc, same as our malloc function. We want to allocate n things, and each of those things is of that particular size. Give me that many bytes, n times size of 64-bit int, which is 8 bytes. 8n bytes, initialize all those values to 0. In terms of our memoization, we actually do know a couple values already. Results of 0 is equal to 0. Because when we're calculating Fibonacci of 0, it's 0. That's just given by definition. Likewise, results of 1 is equal to 1 here. And how many things are actually valid are 2. We have 2 things in our table to start with. The first value is 0. The next value is equal to 1. Now when we're inside our Fibonacci function, we would still have the recursive case here. I'm just going to comment out this previous version, although it's still valid, to kind of walk through a little bit more slowly what would happen when we have this recursive case here. My comment for this would be, if we've already calculated the value, just return that value. So if our value of n, as we're calling this function, is less than that count of how many values we've already calculated. It starts off at 2, it's going to grow here. Just return it. That's our memoization. We already calculated results, or Fibonacci of 0 and Fibonacci of 1. When we get to a function call of Fibonacci of 0 or Fibonacci of 1, stop the recursion right there. We have the value. That's become our new base case here. Otherwise, we should still do that recursive call. So let's add the comment here. Otherwise, do the recursive, that doesn't sound very formal, do the recursive call and keep track of the results for next time. So to do that, I do want to store the result directly. We'll just call that result. And that is going to be the recursive call. I got to think about whether doing n-1 first would be any better than doing n-2 first. That's up to the compiler anyway. Take the result of Fibonacci of n-1, add it to the result of Fibonacci n-2, store it locally now as a result, and update our table is equal to result. And we should probably then increment how many valid results we have, and we do it to make sure we actually still return that result. It's the same as our previous recursive case that we had up there before. We're storing the result as a temporary variable and returning that so that we can also, in addition, update our table. I call Fibonacci of 5, going back to our call stack here. The first time I call Fibonacci of 5, or let's do 4 instead, excuse me. The first time I call Fibonacci of 4, I do the whole recursion thing. But then the next time I call Fibonacci of 4, I don't. I'm done. I've already calculated it. I don't need to calculate it again. Okay, should tell me when I have errors, because it's called, name your variables something better than what I do in class. It's called result count. Hopefully you've gotten better on your own. Like when you get a compiler error, it is always telling you what the issue is, but it's sometimes using compiler, formalities and can be hard to see. In this case, it does say, hey, on line 22, line 6, line 43, you're calling this thing results count. Are you sure you didn't mean result count? It's even trying to fix the error for me, and that was the bug in that case. But it tells you what line it got confused on for that kind of error. Still unhappy because I did call it result count. So let's change it in all places to result count. Results count, result count. I don't like the name of it either. Okay, either way, we'll stick with it. Finally compiles. Now we want to run main with, what did we try it with? 128. There is still recursion. To calculate Fibonacci of 128, we still have to calculate 127 and 126. The only difference now is we've along the way, we've calculated a cheat sheet. We said, hey, I already did Fibonacci of 17 once. Why do it again? Why go through that whole recursion for calculating Fibonacci of 17 again? I can explicitly check that. If I've already done 17, just return the value. Don't do it again. And now we can see the result. It's a pretty big number, but it's basically instantaneous again, right? And now we are still recursive. It's still a recursive solution here. And you can kind of see what's happening, that when we call that inside function, some of this is going to be compiler dependent, and so I don't think you can necessarily guarantee that's the case. The call stack, the printf debugging looks a little bit different in this case because there's the first recursive call and then there's the second recursive call. I guess in practice is what happens is this entire first recursive call always gets executed first. I don't actually know if that's guaranteed or not, but that's the case for this particular implementation of it. So we see the whole recursive call stack from 128 all the way down to, should be 0, right? And then along the way, we then see Fibonacci of 0 returns. Then we do Fibonacci of 1 because as we were going down the stack, there's the 2 branches of that stack. Another way to visualize what's happening is it's basically kind of a depth first traversal of this tree. We go all the way down the left-hand side, and that would include Fibonacci of 0. It's not all included here. And then only when we're done with this side do we then start to handle the right side branches of that recursive sequence. So that's why you see that kind of interesting pattern of our printf sequences there. Questions about this example and our now significantly faster Fibonacci code? Okay. Let's try our own example. If we don't get through it today, we'll finish it on Wednesday. Another very common or famous recursive algorithm is for greatest common divisor. So GCD, or greatest common divisor of A and B, is the largest integer that divides both A and B. Very quick conceptual mathematics check. GCD of 4 and 8 would be what? Ah, very good. Okay, if you got it, you're in good shape. 15 and 25 would be what? 5, okay. Largest integer that evenly divides both values. So 5 is the largest thing that evenly divides 15 and 25. And then oftentimes you'll be interested in knowing, are two numbers relatively prime to each other? What's the GCT of 16 and 35? Right, because we can calculate all the divisors of 16, 1, 2, 4, 8, 16, all the divisors of 35, 1, 5, 7, 35, and there's nothing in common other than 1. 1 is always guaranteed to be a divisor. Those two numbers are relatively prime. There's all sorts of ways one can calculate the GCD. One very historically famous implementation is so-called Euclid's method from the 4th century BC, still valid. You will see this in various implementations for calculating the GCD. We could walk through pencil and paper in this, but I think it's sufficient to say this approach works and can we implement it in code? So I'd like you to take the remainder of our 5 minutes today and partner up. If you're sitting on an island by yourself, physically move yourself to be joining other people. And can we implement this? It is given a base case, which is if the value of b equals to 0, just return a. Otherwise, 2 different recursive cases that are possible here. And that's it. Let's give it a try. So chat with the person next to you, workshop through this. What would it mean to implement this? It should look not that different from like the factorial or the Fibonacci example without all the clever memorization of results, just the pure recursive implementation the same. Yeah, Adam, come on up. Join the people a couple rows ahead of you. Let's give this 3 minutes to see if we can come up with this. Nope, all integers for this. This is like integer GCDs, yeah. By the way, my 10-year-old, and you know, he's a wonderful young man, and one of the real values he provides to me personally is laughing at all my bad, like dad jokes, and he always knows when I'm trying one, and he laughs even if it's not funny. So someone has to take on that role in this class. It's not too late. So whenever you see a lame joke, somebody just has to go ha ha, just so I know that it landed. Okay, thank you, Didi. That'll be you going forward. We only got a couple more weeks of them, but it's not too late to have that added value to the class. So let me suggest there's 2 different parts of this solution. One would be, well, I guess inventing this from scratch is probably awfully clever, too clever for us. Walking through in pencil and paper why this works is also something we could do. But implementing this, assuming it is correct, should be a very kind of like line-to-line kind of direct translation. For our recursive solutions, we usually want the base case first. We're done recursing or continuing to call the function if we've reached that base case. Yeah, I guess we have to use equals equals if it's C code and not like mathematical description, but that should be just one line in our code. There's then a check to see if A is less than B or not, and if that if and else should just be 2 separate recursive calls. I hope it does. Oh, I mean, don't take it up with me. That's Euclid of Alexandria's problem if it doesn't work. I guess in the interest of time, I do want us to go through this example, but let's do it on Wednesday, and that's fine by me as well. So please come back on Wednesday. We'll confirm whether or not the 4th century BC mathematicians got their math working correctly or not, and we will solve that mystery on Wednesday together. Thanks.